Now we'll see characteristics of transmission lines. A transmission line is a pair of parallel conductors exhibiting certain characteristics due to distributed capacitance and inductance along its length. When a voltage is suddenly applied to one end of transmission line, both a voltage wave and a current wave propagate along the line at nearly light speed. For the purpose of analysis, an electrical transmission line can be modeled as a two-port network as shown in figure. In the simplest case, the network is assumed to be linear and the two ports are assumed to be interchangeable. If the transmission line is uniform along its length, then its behavior is largely described by a single parameter called the characteristics impedance, symbol capital Z suffix 0. This is the ratio of the complex voltage of a given wave to the complex current of the same wave at any point on the line. Typical values of Z suffix 0 are 50 or 75 ohms for a coaxial cable, about 100 ohms for a twisted pair of wires, and about 300 ohms for common type of untwisted pair used in radio transmission. When sending power down a transmission line, it is usually desirable that as much power as possible will be absorbed by the load and as little as possible will be reflected back to the source. This can be ensured by making the load impedance equal to Z0, in which case the transmission line is said to be matched. A transmission line is drawn as two black wires at a distance x into the line. There is a current I of x traveling through each wire, and there is a voltage difference V of x between the wires. If the current and voltage come from a single wave with no reflection, then V by I equal to Z0, where Z0 is the characteristics impedance of the line. Some of the power that is fed into transmission line is lost because of its resistance. This effect is called ohmic or resistive loss. At high frequencies, another effect called dielectric loss becomes significant, adding to the losses caused by resistance. Dielectric loss is caused when the insulating material inside the transmission line absorbs energy from the alternating electric field and converts it to heat. The transmission line is modeled with a resistance inductance in series with a capacitance and conductance in parallel. The resistance and conductance contribute to the loss in a transmission line. The total loss of power in transmission line is often specified in decibels per meter and usually depends on the frequency of the signal. The manufacturer often supplies a chart showing the loss in decibel per meter at a range of frequencies. A loss of 3 decibels corresponds approximately to a halving of the power. High frequency transmission lines can be defined as those designed to carry electromagnetic waves whose wavelengths are shorter than or comparable to the length of the line. Under these conditions, the approximations useful for calculations at lower frequencies are no longer accurate. This often occurs with radio, microwave, and optical signals, metal mesh, optical filters, and with the signals found in high speed digital currents. Thank you.